This week with the snow day. So I'll push the test date back a day or back a class period, so it'll move from Tuesday to Thursday. So today we'll finish up 5-5, and then Tuesday next week will be like our review day or whatever. So you just guys we'll be a day behind the A-day crew, but there'll probably be another snow day or something, or I'll find a day next chapter where just like you guys have something that is done at home and they just have something that's due in class and get everything synced back up. But this, with the test coming in, it feels like a dumb time to just try to like rush you guys through it to do that. You know what I mean? So we'll just do it that way. Everybody cool? Okay. I think everybody's here also, right? Oh, yeah. You guys and Amanda. Amanda Roth? Yeah, that's fine. But like, you guys do me a favor and nobody tells Sergio that the test day is moved. Okay? Because he kind of, with as far behind as he gets, he probably needs a little kick in the, to get moving. So don't tell him that anything's been pushed back. Okay? Now that's just not fair.
Yeah. Because he will, and he'll just keep pushing it back. We help. I'm sticking to it, I'm not going to help.
Yeah.
She's going to skip Tuesday.
All right. Let's finish up 5-5 here today. This probably won't take more than 30 or so minutes. And then maybe at the end we'll do questions. I just want to get through this and make sure that I don't forget to do a part or whatever. So in section 5.5, we've been talking about U substitution. So remember that U substitution is a way of going backwards through a chain rule problem. The indicator that we're looking for is where you have one function inside of another. That's our big cue that this is a chain rule problem or is a U substitution problem. Now, if we look at this example here with tangent, where's the U substitution supposed to happen on this? Great, yeah, so we can write tangent as sine over cosine. Okay. And then what do you want to do here? As far as which one of these two, sine or cosine, should we pick as our U? Cosine, because it's the one that's like inside the denominator, so it's like inside of a 1 over. Yeah, that's what I would do as well. So we take the derivative of U. What's the derivative of cosine? Negative sine x. And then our leftovers here is, right, we have cosine that's taken up by U. We have sine and dx. So that's what I want to get on one side. So I'll multiply both sides by dx and then divide by -1. So if I plug everything in now, I'm going to have negative the integral of 1 over u du. Sure thing, Victoria.
You couldn't just do this as like an indefinite integral? Or
Well, what's the antiderivative of tangent?
yeah.
We don't have a rule for it, right? So it's not on our set of rules because the derivative of sine, cosine, tangent, cosecant, secant, cotangent. None of those is tangent, right? So that's why we're going through this. But that's an excellent question, right? Why didn't we just start by doing the antiderivative directly? And it's because we don't have a rule for it. Now, with what we're doing here, could we now add this, what we've done, to our list of antiderivatives and use it in the future? Yeah, for sure we could, but we're not finished yet. So what's the antiderivative of 1 over u? Natural log of absolute value u, and because this is an indefinite integral, it gets a c at the end. And then we're not done. What do we still need to remember to do? Plug in the u. What was our u again? Cosine. Okay, and now I'm going to use, now this is correct what I have here. I'm going to use a little bit of log rules to get a slightly more attractive final answer. So I have a -1 as a coefficient on my logarithm. So I can move that -1 into the exponent inside the logarithm. What's the reciprocal of cosine? 1 over cosine, or secant. So the way this would typically be written would be the natural log of the absolute value of secant x plus c. And that, if you wanted to, you could use this as an antiderivative rule in the future, right? You could add that to your list, that the antiderivative, or the integral of tangent x is the natural log of the absolute value of secant x plus c, right? Yes? Sure. Okay. So now what we're going to do is we're going to do some definite integral problems with u substitution. And the obvious thing would be like, well, I'll do it the same way, right? I'll just do my integral, substitute back in, and then evaluate at the bounds. And you can do it that way, but there's a shortcut that makes life a little bit simpler. So the shortcut here is presented in this theorem. And it just says that the integral, or the definite integral from a to b of f of g of x times g prime of x dx is g of a, or the definite integral from g of a to g of b f of u du, which is a much simpler definite integral to evaluate, right? And now this looks messy. It's really not a problem at all. I'll kind of give you, or I'll show you what's going on here in just a quick sec, okay? With these examples, because it's, when we actually go to apply this, it's quite easy to do. So again, we're going to start by our typical u substitution. What would the u in this case be? 2x plus 1. Excellent. And du dx then should be 2. If I look in this problem, the u I have covered. My leftover is just dx. So I want to get the dx alone on one side. So I'll multiply both sides by dx and then divide by 2. And I'll put the 1/2 out front. I'll leave the du there. Now what I've written is technically not correct. What's wrong with this? The bounds for my integral are with respect to x. I now have a u. Taylor?
Where's the 1/2 come from?
The du over 2. I just put it out front. So what I need to do is I just need to change those bounds so that they're with respect to u. So all I'm going to do is like u of 0. So I'm just going to plug 0 in. And I'll do u of 4. So I'm just going to plug 4 in for u, into u, or in for x, I should say. So those bounds should really be from 1 to 9. Everybody's okay with that? So now I'm going to go ahead and do my antiderivative. What's the antiderivative of the square root of u? Yep. And I'm just going to write it that way where I've already done the flipping. And now I'm not going to substitute back in for u because the bounds I have are with respect to u. So I can just plug those values into the u and be done with it. Much simpler. So I notice here I can do a little reducing before I do that. So I have 9 to the 3 over 2 over 3 minus 1 to the 3 over 2 over 3. What is that? 9 to the 1/2 is 3. 3 to the 3rd is 27. Divided by 3 is 9. So it's like 9 minus 1/3. Or what, 26 thirds? And again, just a little bit simpler computationally than having to plug the x's back in and then plug those into x's, because the expression is always going to get more complicated when you sub the x's back in, right? It's just more arithmetic to have to handle. Is this okay? What do you notice? That this is still basically the same thing, right? We just added in a step where you just plug the bounds into the function for u and get new bounds, and same problem as before. All right, what do we pick for u? 3 minus 5x, I agree. You could even pick 3 minus 5x squared if you wanted to. That would be okay also, but I probably wouldn't do that. So the derivative there is -5. My leftovers is just going to be dx, right? So to get dx by itself, I'm going to have du over -5 is equal to dx. Okay, and then we have to find our new bounds. So 3 minus 5 is -2. 3 minus 6, or 3 minus 10 is -7. So this is the integral from -2 to -7. 1 over u, and I guess I'll put the -1/5 out front, du. Oops. Not 1 over u, Mr. Kulik. U to the -2. Sorry. Or 1 over u squared would be fine, but I'm going to write it that way because it's a little bit more obvious what the antiderivative is going to be if I write it that way.
Would there be a problem since the lower bound is greater than the upper bound?
Yeah, so there's no real problem, but what can we do to fix that? You flip it and make it negative, right? So the negative on the 1/5 is just going to go away. We can flip the bounds. It looks more natural that way. You get the same answer though if you had left it. Still be fine. So now it's just antiderivative time, right? What's the antiderivative of u to the negative 2? U to the negative 1 over negative 1. Going from negative 7 to negative 2. So if I plug in negative 2, what's the reciprocal of negative 2? Negative 1/2. And divided by negative 1 is going to be positive 1/2. And times 1/5 is going to be 1 over 10. And then minus the reciprocal of negative 7 is negative 1 over 7. Divided by negative 1 is 1 over 7. Times 1/5 is 1 over 35. And then what do we do there? It's going to be 7/70 minus 2/70. So that's 5/70, which reduces down to 1 over 13. No, 14. Thank you. I know I didn't make the least common denominator there, but it was like an easier to deal with than making the. But oh, maybe that was the least common denominator. Anyways, it was an easy denominator to make. Everybody's okay? Worth pointing out, all these problems that we've done with the definite integral are all checkable on your calculator, right? You use the fnint command and you can evaluate all these definite integrals to get the decimal answer to check. Paul?
Can you show us that again? I kind of forgot that.
Sure. So I think the best way to do it is I'm going to start by taking my integrand and just typing in the y equals. Now, obviously, I don't include the dx. So I just have 1 over 3 minus 5x squared. I'll exit out of here. Then I go to the math menu. I scroll down to the bottom and I'm looking for the fnint command. So that's function integration. So I'll type in my bounds. Those were 1 and 2. My function I typed into y1. So I do vars, yvars, function, y1. And then we used x's, so I'll just do dx. And then I press enter. And I get this, and if I hit math frac, 1 over 14.
Thank you.
It's math, and then you go down to like command 9 or something. It's called fnint, function integration. So all of our calculators, not just the fancy CAS ones that can do the indefinite integrals, but your guys' calculators, everyone's calculator can do this. Alternatively, instead of using like y1, you could have typed that in the function directly in here. And on this problem, there's really no difference between doing this. But if you have like a lot of different stuff to do, oftentimes it's nice to just type into the y equals to get a picture or whatever of what you're doing, and like you might have other stuff to do with it, but you could type the function directly as well. You don't have to type it into the y equals and then reference it. That's just the way I like to do it. Is that cool? It's in my pocket. Oh. Very important drawing from my daughter. Just like some scribbles on a piece of paper. All right. You ready to do the next one? Okay. Let's do it. All right. What should I pick as the u here? I would pick the natural log. That seems counterintuitive. But what I'm noticing is I know the derivative of the natural log is 1 over x, which is the other part of my leftovers, right? So if you chose wrong, you're just going to have something like your leftovers just aren't going to work out. And you probably would know to go back and try a different u if you tried 1 over x or just x. Probably wouldn't have worked out for you very well. Okay, and then we have to do u of 1 and u of e. What's the natural log of 1? That's 0, very good. And the natural log of e is 1. Well, hey, that's just right there. That's kind of an improvement. And look at this, what this integral turns into. That's lovely, right? So the antiderivative is just u squared over 2. Oops. So I just have 1 squared over 2 minus 0 squared over 2, which is just 1/2. Looked like a pretty scary integral there to start with, and that turned into pretty darn easy. So the next, or the last topic here in chapter 5 that we're going to talk about is this theory on the symmetric integrals of symmetric functions. And this is another one of these theorems that we'll use a lot. This is an important one, or a quite useful one. I guess not important because you can do it without it, but it's a time saver for sure. So it says if f is even and we're integrating from negative a to a, then we can just do 2 times the integral from 0 to a. Or really, you could have done 2 times the integral from like negative a to 0. That would be okay too. So to just kind of remind you of what's going on here, if you have an even function, that means it's symmetric about the y-axis. So what this is saying, if I'm integrating from like a to a, that area and this area have to be the same, right? So I can just do this area twice. Or I could do that area twice. Same thing, right? Since the even function is symmetric about the y-axis, and we're doing the same amount before the origin and after the origin, it's the same areas. Everybody okay there? The other part of this theorem says that if f is odd, again, we're integrating from negative a to a, just going to be 0. Again, to remind you why that's the case, an odd function has that 180-degree rotational symmetry about the origin. Do a better job of drawing that. So if this is, again, negative a and a, this area down here is negative, but it's the exact same quantity of areas over here. So when you add them together, you get 0. Is everybody okay with that? So the hard part about using this theorem is just boils down to, can I identify whether these functions are odd and even? So let's practice doing that. So let's say our f of x here is x to the 6th plus 1. To check if they're odd or even, I do the composition with negative x. So negative x to the 6th is even, or is positive, because it is an even number of negatives. And that is just what we started with, the original. So we know that this is even. So this is just the same as the integral from 0 to 2. So if we wanted to integrate this, then we'd have x to the 7th over 7 plus x evaluated from 0 to 2. So what's that? 128 over 7 plus 2 minus 0. Whatever that is. I'm not doing the arithmetic. I don't care enough.
You have applied that way.
Oh, yeah. Perfect. Yes, thank you. Yep. Good catch. I got so excited. Forgot it. Easy to do. It just happened to me. Teagues, what's up?
No.
Oh, okay. Those are my favorite kind of questions. All right. Take a look at this one. Again, I noticed the bounds are opposite. That's my cue that I should be trying one of these things. And I'm really hoping that this one is odd, because I look at this and I have no idea how to do this integral. So my f of x is just going to be tan x over 1 plus x squared plus x to the 4th. So f of negative x is tan of negative x over 1 plus negative x squared plus negative x to the 4th. Okay, trig identities, tan of negative x is negative tan x. And then I have over 1 plus x squared plus x to the 4th, which is negative of what I started with. So this is odd. So just 0. That's pretty handy, because I had no idea what to do with that. That's not a U sub problem. It's a big problem. But since the bounds were opposites and I had an odd function, I could still do it.
So if you had arc tangent, would that be an even function?
That is odd also. Because if you think about arctan, you go from like -1 to 1, I believe. It looks like this. Something like that.
So would that be uniform over all the arcs and tangents? So tangents odd, cotangents odd, and arctangent.
Yeah, I think you could say that. So what this boils down to is, can I predict? Like I can do the f of negative x to predict or to figure out if the things are odd or even. Mr. Kulik can look at these things and tell without doing anything, just in my head, no function composition. Let's talk about how you go about doing this, right? All right, so a couple of basics. We'll do like just odd, even basics. So sum of odds is going to be, if I add up a bunch of odd functions I get, it's going to be an odd function, right? If they're all odd, when I do the composition, they all get a negative sign in front of them, which makes the whole thing have one negative sign in front of it, which makes it an odd function, right? Sum of evens is even. If I have odd function divided by an even function, what's that going to be? That'll be odd. If I have an odd divided by an odd, that's going to be, that becomes even, right? Because they both get a negative sign in front of them and then they cancel out. If I have even over even, well, that clearly just has to be even, right? And then obviously if I add even over odd, that has to be odd also, right? The multiplication ones are the tougher. Odd times even is odd. Okay. Odd times odd is even. Even times even is even. How about actually we'll do it this way. Product of odds is going to be even when what? An even number of odds, yes. And they'll be odd otherwise, which is just when you have an odd number of odd functions multiplied together. And the product of any number of even functions is just going to be always even. Everybody's okay with that? So on site, let's make a list of some notable odd and even function types. Bless you. So we say a monomial is odd when would a monomial be an odd function? That's like x to the first or 2x to the fifth or 7x cubed or 9x squared. The degree is odd, yes. Okay. And we say a monomial is even if the degree is even. So if I have a polynomial where all the terms have odd degree, I know that's an odd function. And if I have a polynomial where all the terms have even degree, it's an even function. That's how I'm able to look at that polynomial and see immediately that that's even, because I have x to the 0, x squared, x to the fourth. I know that's an even function right there on site. 1 is x to the 0, right? Right? It's a basic fact. I've just given a second to process. Okay. Trigs. Sine and tangent are odds Cosine is even. And so that also would extend to the reciprocals, right? So like cosecant and cotangent also odd. Secant also even. Arcsine and arctan are both odds. I don't think arccosine is defined as even because it's from 0 to pi, so it's not, there's no symmetry between the, at the origin there, where the arctan and arcsine are defined from negative pi over 2 to positive pi over 2. So I know that those have the symmetry you need. I don't think arccosine is even though. But usually that's enough right there. What if you have like an odd plus an even? Or yeah, what's an odd plus an even function? No. 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 Neither. For example, if I have x to the third plus x squared, if I did f of negative x, I'm going to get negative x cubed plus x squared. That's not the same thing as f of x, and it's not the same thing as negative f of x, right?
Can you repeat the thing you said about the polynomials and monomials? Like, if the polynomial, can you repeat that?
Yeah, so if the polynomial is each term is odd, the polynomial is an odd function.
Okay.
If each term is even, then it's an even function.
What if there's both?
Then it's neither.
Okay. But in that one, it was odd.
This one is, no. We're looking at each term. I have an odd term plus an even term.
So it's neither.
That's neither. If I have all odd terms, then the whole thing is odd. If they're all even terms, the whole thing is even. If you have a mix of both, it's neither.
Okay. But in the last example we did.
You're talking about this one over here?
Yeah. Oh, we had two.
This is even also.
It is.
Yeah, because I can just tack an x to the 0,
Oh, that's odd. Okay. But
right?
So it's even, but we got an odd.
Right.
So it's 0.
Well, because I have odd
Up there.
over even.
Okay. Good job.
So it's odd, which is why it's 0. And I can tell on site. Right? Again, do you have to be able to tell on site? No. I'm just trying to tell you, like, if you're doing a multiple choice AP test, like, it's helpful to be able to look at a problem, just know what the answer without having to justify anything, because you don't need to justify anything.
If it was like cosine on the top, would it still be odd?
No. Because
Why?
not cosine's an even function.
And sine's an even function?
Sine is odd. Tangent and sine are odd. Cosine is even.
Oh, okay, that's what you put.
Yep.
Nice.
So if it was cosine on top, this would be sine over.
It'd be an even problem where you'd have no chance of doing the integral without a
I
calculator.
can do that.
But odd over odd is even. Sine over tangent. Oh, you said sine or
And-
tangent.
yeah.
Oh, I thought
Yes.
it was sine or.
Same.
Oh, sorry. Yeah, did I write a slash there?
Yeah.
Okay, let's change it to a comma. So if you're going back and looking at that. There we go. That's a heck of a lot more clear. My apologies. I just got rolling without pre-prepared notes. Isn't it amazing that all that stuff kind of just lives in my head and just can shoot it out at like 100 miles an hour? Well, you study mathematics for like 20 years and come back and talk to me, and you'll have the same thing. It's not like a superpower. It's the result. It's the same way that like a concert pianist has a superpower. It's like, no, they've just practiced this for 20 years. So like what seems superhuman to you is just the net result of like thousands of hours of practice. Paul.
Are you Dr. Cool yet?
The hope is that can complete that this fall or this spring. So, well, I won't have the graduation. I think will have happened before then, but I'll have finished everything by then.
Yeah, can we call you Dr. Cool?
You can do whatever you want.
It's a college level class and he has a doctorate, so I call you professor.
Sure. So that's it for 5.5. Notice that I made you guys a test review. I assume that most of you guys made it or have noticed that already. I would point out to you that that I made some updates here from when I originally posted it. So if you moved it into your content library long ago, delete that one and move the new one in, because these problems over here, there were some typos on that I had to fix. Just FYI. All right. So the format for your test will basically be the same as the review, probably a little shorter. At the front, I just have like list of skills that I'm going to be testing on, and then I have examples of these skills. So like if you want to evaluate this integral and you're given this picture, what do? Count boxes, right? Just remember that these boxes down here are negative. And because you're going to be approximating things, I would say just approximate to the 10th. And Mr. Kulik will be reasonable as long as you have like a reasonable estimation. We're not going to quibble if I said something is 0.7, you said it was 0.6 or 0.8. Now, if you called it 1, I'd have a problem with that. If you called it 0, I'd have a problem with that. Or if it's clearly like 0.7 or 8 and you called it 0.2 or something. But if, you know, like we're talking about a 10th or something difference, I'm not going to worry about that kind of thing. Here we're just converting from this form into an integral. I think almost every practice ACT multiple choice question I've looked, or multiple choice exam I've looked at had some problem kind of this type. Do you know how to do this? Guys, here's the deal. This was just a definition. This was like definition 2 from this chapter. So this is equal to the integral from a to b of f of x dx. Okay. So from looking at this, I can identify this as my delta x, and this guy as my xi, and this as x cubed, or a cube root of x, right? So remember that delta x is b minus a over n. So this just tells me b minus a has to equal 9. Xi is a plus I delta x. So that tells me the a is 7. So if a is 7, b has to be 16. Well, b minus 7 has to equal 9. So I just have the integral from 7 to 16, cube root of x dx, and I'm done. Right? Just purely testing you if you know the definition of these things. Which is lovely because you don't get an equation sheet, so you legit have to have that memorized. I know. But it's like it's an easy question to do once you know how to do it, right? What's the multiple choice shorthand? A, B, add them together, and then F is just the function. Like I don't need to write anything down. I wrote all that stuff down so like you understood where I was getting it from. But that's all I'm doing. A is 7, B b is 7 plus 9, the function's a cube root, done.
Really, that's how you think.
Yeah, that's what I see when I look at it. I'm just looking for what is this, and what's the function.
Okay.
That's all I'm doing. Like I wrote all that stuff down so I can justify you like why those are the only 3 things that matter, but that's all that matters. It should be like when you understand what to do with this, it's like a 30-second multiple choice question. Right? And then I have like rewrite the integral as that limit of sums. So it's the same, just using that same definition, just unpacking it the other way. I have a Riemann sum problem where I give you a table of values to compute your Riemann sum. Does it matter that those are not the same change? No, it just means your rectangle have different bases. Big whoop. Doesn't matter. Calculate the definite integrals. What am I noticing here on the first one? The bounds are opposite with an odd function, so it's 0 right away. Again, this one, the bounds are opposite, but this is an even function, so it's just 2 times half of it. So just 2 times that. Done. Right? Like, what am I going to do with this one? I'm piece it together, right? Like the limit or the integral from 8 to negative 3, and then plus the integral from negative 3 to 2 should be the limit, or integral from 8 to 2. Easy.
What do you mean 2 times half of it? 2 times and half of that?
No, this is half of the integral, right? Because I only went from negative a to 0.
Oh, is that 0?
Yeah. So the original problem is from negative a to a. Half of that integral is just from negative a to 0, or from 0 to a. Either one of those is half of it.
And you know it's even because there's 4 and cosine.
Yep.
But the other one on top is odd because
Tangent's odd. And 4 is even. Yep. Paul?
Never mind, I figured it.
Okay. What if I asked you to compute this integral? And I'm just giving you the picture. It's geometry, man. You're just making rectangles and triangles and adding them up. Or subtracting it for the stuff below. Be careful about that. Easy to forget to subtract. But it's just like a crummy geometry problem. Big whoop. What about this one? Yeah, just FOIL it out and you're doing the antiderivative and plugging stuff in, right? No big deal. Notice that basically this first half was like, what are the different ways I can evaluate an integral? Like, here's some shortcut theorems. Here's what you can do if you're just given a table of values. Here's what you can do if you're given a function with no grid. Here's if you have a function with a grid. Here's just an equation. Like, just different ways to evaluate a definite integral. Yeah.
So going back to the one where you're just making your own like geometric shapes and counting that way, what if so if you look at like the 0.62, what if that wasn't in the domain? So it was like an open circle.
Oh, so if you just, the endpoint was open?
Yeah.
Doesn't matter.
It doesn't matter.
Doesn't matter. If you think about, like, if I have a square like this, if I don't count the edges, does it still contain the same area?
Yeah.
That's what you're saying.
Okay.
That's what it would mean. So even if like some intermediate point was open, doesn't change the problem. Still just adding areas. In fact, all the intermediate points could be open. You know, like all the corners or whatever could be open, or there could be openings all over the place. As long as there's finitely many of them, it's still the same. If there's infinitely many of them, then you have a problem. But that's like a real analysis kind of problem. Not a high school AP calculus problem. And then I just have some indefinite integral problems. So these are just like regular antiderivative problems, or maybe U sub. some of both kind of mixed in there, whenever, wherever, however. But that's the gist of it. Should be a pretty narrow and focused exam, right? All we're doing it really is doing integrals just over and over and over again. We're just Mr. Gulick's just gonna test you to make sure that you can do like all the different ways I could ask you to do the integral. You can do all those different ways, you know? Whether you're approximating or like finding exact, but you're doing geometry to do it, or you're doing it using calculus or whatever. It's all kind of the same problem, just different technique based on what you're given. Do you guys have like regular old some homework problems that you want to talk about? We got whatever, half an hour or something left. You got some? Hit me, Victoria. 5.5, number 15. Sure. So we have the indefinite integral of sine of pi of t dt. So my u should be pi times t. Du dt is just going to be pi then. If I look at my leftovers, that's just dt. So to get dt by itself, I'm going to have du divided by pi is equal to dt. So this is the integral of sine u, and then we'll stick the 1 over pi out front, du. The antiderivative of sine is? Okay. That's okay. That's okay.
Why? Like, there's a pi in the equation.
Yeah.
Or is there not?
Yeah, pi times t. So I said u is pi times t, so that's just u. And then I have that dt is du over pi, so I have du, and then I have the 1 over pi out front.
Oh, so we would have to divide by pi because that pi that's already in there is already taken to u.
Right.
Okay.
Yep. So you're looking at the leftovers, right?
Yeah.
If you have to do it as like, put the u in and leave everything else, do that to see what's left, so you're able to kind of move stuff around appropriately. Mr. Gulick takes for granted that like you can see it in your head really quickly, and if you can't, that's okay. Tell me and we can do it like more steps so you can see it. Ideally, you'd get to the point where like you can just see it and go, but I need to remember that this is the first time that everybody's doing this, and even though I think it's easy, it's not easy. Slow down, you goof. Okay, and last, we're just now taking the antiderivative. What's the antiderivative of sine? Negative cosine, excellent. We have the plus c, and then I'll just regular substitute everything back in, right? So u is pi t. I'll just write that over pi plus c. Yeah, go ahead.
23.
Same section?
Yeah.
Okay, no problem. If I'm going too fast on things, please stop me, ask some questions, tell me to slow down, ask me for an intermediate step or something. All right, let's see. Ooh, this one's sneaky. All right. What do you want to pick for you?
I think it's 10. But I don't know.
I would not pick tan to the third. I'd pick just tan. Sure. Sure. And the reason I like this is what's the derivative of tangent? Secant squared, right? Which I'm thrilled about because that's my leftover. So if I plug this, if I just plug in the u, I have that, right? I can see then that I can make my du secant squared theta d theta.
Wait. You have secant, so your leftover is secant, so the du would just take over secant. But why is like tan still like third 3?
Well, again, u is just tangent. So I have u to the third, right? And then my leftover secant squared d theta, I was able to turn du into that. So I'm all good. So I just do my antiderivative. I have u to the 4th over 4 plus c. And I just plug my u back in. And then what were we doing? Thetas over 4 plus c. So again, if you're going and doing this and you're having to do like a chain rule or a product rule for your u when you're differentiating your u, you probably picked the wrong u. More often than not, it's going to be simple to do that derivative. It should be simple because it's probably the result of an easy chain rule, because we're not going to ask you to do like, I don't think there's going to be like a, even in the homework anywhere, I don't think there was a double chain where you had like, you had to pick your u and then what you're left with, then you had to do another substitution inside of, and that can happen, but like I don't think that's, I didn't see that happen anywhere. I don't think I've even come across seeing it on an AP exam anywhere. Be a fair Calc 2 college question, but I remember doing it at one point in college sometime. I mean, that was 20 years ago, so like, who knows? But, all right. Victoria, that was your 2. Does anyone else have some stuff from chapter 5 they had still want to talk about? Homework problem-wise? Okay, that's fine. Reminder again, so Tuesday next week, we're just going to have a day to review, so just come with questions, and then after that I'm going to leave you alone and let you work on what you need to work on. But I don't have anything focused planned for it. I'm going to let you guys kind of self-direct. So whether they're homework questions or review questions or whatever, or if you want me to, I can dig up some like AP questions related to this kind of stuff that we could do. Whatever you want is fine with me. Maybe I'll have that as a backup or something. You guys cool? Okay, I'm gonna stop here.